next presentation, I would like to welcome Lukas. Lukas is from the Austrian Institute of Technology, and he's going to talk about high-speed inline computational microscopy systems for industrial inspections. So great to have you here.
Hello, thank you for the introduction, and thank you for the invitation. So I want to talk about high-speed inline computational imaging for microscopic resolutions. My name is Lukas Traxler. I'm from the Austrian Institute of Technology. It's the largest non-university research institution in Austria. And I'm working at the Center for Vision, Automation and Control. So we are building inspection systems which serve the automation of certain industry areas. So why do we need microscopic imaging? Here I have an example for that. What you see here in the picture is a microelectronic ball grid array. And this microelectronic ball grid array, you see it in size, it's quite small. It has 10 by 10 millimeters. And it's important to inspect all these soldering joints. And there are like a couple of thousands of soldering joints on this particular device here. So you need a quite high resolution in the 1 micrometer range to resolve the height differences to inspect the proper working of this microelectronic device. And if you think about rapid production cycles, you have to scan such devices in a very rapid way. So if we consider that we would have a sampling of 700 nanometers per pixel, then this would mean for this very small chip of 10 by 10 millimeters that we would actually need 100 million 3D data points. So the question is, how fast can we inspect just such a surface in such a high resolution in a very fast way? And from 3D microscopy, you might know different approaches on how to solve that. One, for example, is depth from focus. Depth from focus, it builds on the effect that for high optical resolution, the depth resolution, the focal depth is quite short. So if you do a Z scan through the object, then you can stitch together all the planes where you see in focus information and gain a 3D information from that. The problem of that is that it's quite slow, as you see on this exemplary image, that actually most of the image is out of view, out of focus, because just one part, one depth of the object is in focus. If you think about confocal microscopy, most of the time it's a point-to-point scanning process, so you have to scan for every individual point. There are fast point scanners, but still this is quite slow if you scan large areas. There are also confocal line inline inspection devices available. They go down, what you see right now on the market, down to 2 micrometers in sampling, to point-to-point spacing. And also white line interferometry would be a possibility, but still you need here a scanning process for the interferometer, and this still requires that the object stays still for the inspection, and it can't be easily implemented in a non-stop continuous motion process. So we try to address this problem of 3D microscopy with another approach, and this is our in-house developed inline computational imaging framework. So what do we mean by inline computational imaging? By inline computational imaging, we mean that we gather different imaging modalities, combine them together, and deduce data, 3D data from that information. What we'll use here, or what's used typically for that, are so-called light field images. So you view an objective from different angles, and then from the multi-view stereo, you can deduce 3D information. You also can enhance that by so-called photometric stereo, which is illuminating the object from different illumination directions, measuring the photometric response from different directions, and then combining that to a 3D information. As you see here on the left-hand side on this slide, that these light field cameras and multi-illumination direction domes are quite bulky, expensive, and very inconvenient to build them in a very fast inline inspection environment. So for our inline computational imaging system, we strip down all these components to the most necessary parts, and we're using one camera. We're using the naturally available transport of the object, for example, as the object is traveling out of the production line, to get multiple views of the object, and we are using 4 illumination directions to get the photometric stereo response. And this is a system which you can have a look over there at our booth for the macroscopic range, where you can have various field of views. But now what I want to talk today in this talk is how to scale that down to microscopic level. What are the challenges for that? And actually, in scaling down the problem, we have some like physical limitations. First of all, if we think about very high optical resolutions, following from a physical principle, the focal depth is quite short. So it's very hard to get a decent focal range or a decent range of focus in which you can inspect the object. So you have to find a good balance between the necessary optical resolution and the depth range you want to scan. And the second problem is, as you have a very small field of view, and we're actually using the change of the perspective when the object moves through the field of view to get a motion parallax or a stereo parallax effect, it's actually quite hard for a microscopic system to get a decent baseline compared to a stereo camera system, for example. So how did we solve these problems? What we actually did is we developed our own modification of industrial microscope optics. Usually, microscope optics are built in a so-called telecentric way, which means if you move the object beneath the microscope lens, then you wouldn't see a motion parallax at all, so no 3D effect. But by introducing an additional aperture, you can actually shift the point of the projection center, and we shift it in a way that we get a so-called hypercentric perspective, which means that we view the object from the outside. And this is possible because modern microscope objectives usually have a very high numeric aperture, so you have a very large lens diameter compared to a very small object. So you can use the outer rim from the objective lens to get a very large parallax angle on your observed object. This modification is not very trivial, and it has to be tailored to the customer's need. Just for a short introduction on the optical constraints, what you have. So what you basically do in this typical 4F microscope design is that you induce an additional aperture, which induces this special projection. And by choosing the diameter of the aperture, you're actually selecting a certain optical resolution, and you're also selecting a certain depth range in which you can inspect this 3D information. And now there are some constraints. The further you would move away the aperture, the stronger would be the parallax effect. So the better would be the set resolution of your inspection system. But if you are going too far away with your aperture, then you're actually moving your observation outside of the available numerical aperture of your objective lens. So this is actually the constraint, the numerical aperture of your objective lens, of what's the maximum oblique angle you could use to observe the object. And another constraint is to find a good balance between optical resolution and the focal depth you can inspect. So how does this look like now in a real inspection? Oh, now can I switch back? In a real inspection device. So just that you can imagine what I mean by this hypercentric projection, I have an example here. If you think about observing this tooth gear, then a hypercentric projection would mean that objects which are further away from you disappear larger. So it's inverse to your common vision. If you allow looking here into the room, then everything which is further away looks or appears smaller, and here it's the other way around. But that's the better way to utilize the numerical aperture of a microscope objective. So that's how the objects would look like. And now you see, if you observe this object at different positions in the field of view, you see a change in the parallax. And that's why we can do multi-view stereo from the images. Beneath the microscope, we can see an illumination source. It's also custom built. We have 6 illumination directions. This helps us a lot to suppress gloss artifacts. For example, if you do inspection of metallic surfaces, because we can measure the photometric response from 6 different illumination directions, and then find the images which are properly illuminated, which don't show specular reflections, and with that we get very clear and speckle-free images. And also very important component is the stage underneath. So this represents the natural transport of the object. You would typically have that in the production environment, for example, because products are moving out of a production line, or if you would think about manufacturing of wires or stuff like that, then there would be a natural transport of your objects due to the production process. So actually you could use this natural transport of the object as the only and single scanning direction you would need for this microscope principle. So compared to other 3D imaging methodologies, it really is a fully capable inline microscopy principle, because it doesn't require any scanning process. So no Z-stack, no raster scanning or something like that. It just needs one scanning direction, and this is the natural transport of the object. So it really can acquire these 3D images you will see in a minute in a pure static non-stop motion. So with this modified optics, we actually could scale down our inline computational imaging system to the microscopic level, where we have point-to-point point distances of several hundred nanometers, where we can see very fine details. If you are interested about technical details, there's also a publication. This technology is also patented. And now I will guide you through some applications where you can do with that. Before I talk about the applications in detail, I just want to show you some specifications. And if you compare that now to other 3D inspection modalities, like white light interferometry or like confocal microscopy, you will find out that it's completely different because the working principle is so different. So as I mentioned before, in our demonstrator, as you can also see at our booth over there, we have a point-to-point distance of several hundred nanometers. The field of view normal to the transport direction would be 1.6 millimeters. And the field of view in transport direction actually could be infinitely large. It's just limited by how you process the data. So at one point in time, your computer memory will be full of data. But in principle, it's a really continuous process on both sides, on the acquisition process and also on the data processing process. It is a straight pipeline. From the working distance, it's actually quite far away, which is good for industrial applications, so you don't have to be super close to the object. It's 34 millimeters. The depth measuring range is 160 micrometers. You could adjust it to your needs with sacrificing optical resolution. You could also get a better optical resolution by decreasing this depth range, so that could be adjusted to the needs of the application. And what's very special about this system is that this linear motion could go up to a speed of 12 millimeters per second. And if you calculate now with this 12 millimeters per second and a point-to-point spacing of 700 nanometers, that means that our system is capable of acquiring nearly 40 million 3D data points per second, which is quite a huge number if you compare it to other systems, and it's really a non-stop continuous motion. So here are some examples. So what you see here is now this 1.4 millimeter field of view. Our acquisition device acquires the albedo image, so the texture information and the 3D information at the same acquisition process at once. So it's just another like rendering in the 3D representation if you want to visualize it in a color depth map, or if you want to have gradient images or albedo images. And here you can see the level of details on this example here on parts of a coin. And you see it's very resilient to specular reflections and gloss, which you typically have in metallic inspection. Another example would be print inspection. So here are security features from banknotes. Here you see from the intaglio print that you have very low indents in the texture of the paper. And this you can also easily scan. Also here color coded, or you can code the depth in color as you would like it. Here's another example of in intaglio print. So here you actually, in the albedo image, you most prominently see that on this spiral structure you have a different ink. But actually, due to the printing process, from this intaglio printing process, you actually have a different depth of these objects. And now what can we do with this high speed thing I talked about? So with the nearly 40 million points per minute. For this example, I come back to my ball grid array I mentioned in the beginning. So of course, our 10 by 10 millimeter ball grid array is larger than our 1.6 millimeter field of view. But as our acquisition process is that fast, we can actually scan this object in different lanes and stitch them together. So this is the field of view which you would acquire in one single acquisition process, in one single linear motion. And if you now do a scanning process in this direction, then you can easily stitch a larger field of view. And then you can see all these small details. So here you can see all these small solder joints, which in that particular case would be in the order of magnitude of 1/10 of a millimeter. And like on this area, we would have like 3,000 of these connectors. And you can also like go crazy and scan large areas with this really high magnification. And here's an example of a coin. So this is a coin, which, as you can see, has around about a diameter of 20 millimeters. So if you scan that with this high resolution of a point-to-point spacing of 700 nanometers, then you get 1.6 gigapixels of 3D points. So the data amount you have to store is here like nearly 50 gigabytes of data, but you could acquire this with our systems in less than 30 seconds. And that you really see that you have like this level of detail. You could like continue zooming in. So I now just showed you a no-color rendering. And now we could zoom in a little bit, and still this small detail would still contain 2 million points. And if you zoom in further, then I invite you to get to our booth over there, and then you can have a look at these objects at these high resolutions. And again, it's you can also like do different visualizations. It's now again here color coded. And with that, I'm also at the end of my presentation. So concluding my talk, what do we have? We have developed a novel 3D microscopy methodology, which is different to other inline inspection principles. It's fully inline compatible. And due to the multiple illumination direction, it's really robust against gloss on the surfaces. So you can apply it to actually virtually every surface type. So thank you for your attention, and now I'm open for questions or later at the booth.
Thank you, Lukas.
Thank you.
So I don't see any questions so far,
okay.
But I guess people will come to your booth directly. And please, you sitting at home following us, and you sitting here, feel free to ask questions.